I have actually really taken some of my first help, but I can't really have anything. So they do like mess with me. I should memorize a lot of these for me. Symptom rule is a delta over delta x over 3 and the first one doesn't have anything in it. 4, 2, 4, 2, 4, 2, 4, 2. And it has to be an even number of actually subdivisions.
Well, welcome back, folks. Looks like we're ready to get started. Any questions at all before we get going today? I have a lot of announcements, so I think it's best to turn it over to you all first. Okay, well, the big announcement is not the stuff here, more that we have an exam coming up. It's next Monday. So the information has been made official. The exam is going to start in 7.7. This is approximate integration, trapezoid rule, Simpson's rule, that kind of stuff. 7.8 is going to be improper integrals, either type 1 or type 2. And then from then on out, it's kind of grouped. This is dealing with either the length of a curve or the surface area when a curve is rotated about the X or Y axis. In this section right here, I'm not going to ask anything about the hydrostatic force, not because it's a bad topic. I just felt like the book didn't support it too well. I'm mostly going to be asking a question about centroids. Then in this grouping here, now we're in differential equations. I'll ask a question where you have to verify if something is a solution or is not a solution to a differential equation. Then 9.3 will solve a separable equation. 9.5 will solve a linear equation. And then that rounds out the exam. It's a pretty short exam, about the same length as the last one. The last one was more about integration technique after integration technique after integration technique. In a certain sense, I don't think this one is as challenging. 7.7 is just a formula you navigate through. This is the challenging section, in my opinion, this time, because we have to break down the improper integral by determining what made it improper so that we can write down do the integration and do the limit all at once. It's really quite a lot going on. It says my default speaker has changed to L. That was weird. I should double check. How are folks doing over Zoom? Is the audio working still? We could always try to chat. Oh, we got a chat come back. Awesome. Thanks, Kevin and Nick and Easton. So Zoom's still working. I got a weird notification in case you didn't see it that my speakers are suddenly connected. Hopefully they were the whole time. But 7.8 is kind of the challenging, more challenging section. I'm not going to ask you to integrate improper type 1 and an improper type 2. What I'm going to do is really flip a digital coin. So have randomization inform me which one you'll show the complete steps to. And then for the other problem, I'll have you just do the setup, which means convert the integral into a limit and then just leave it like that. That'll make the exam feel not as long. And from here, these problems are really, really similar, right? I'm going to do the same kind of thing. I'm going to really just flip a coin, either ask you a length of a curve problem, 8.1, or a surface area problem in section 8.2, and then expect a center of mass problem here, and then again, verify this differential equation, and then solve 2 more. So that's another view of the exam. And same kind of information like we expect to see from exam 1 is posted down here as well. This page is the real last page on the actual exam 2. They're going to hate me at the testing centers. It's a lot to print. But I mentioned that I'm going to be using a little bit more space on these pages. And this is what it looks like. I'll give you information on sinusoids, trapezoid, the improper integrals. This will be if we're dealing with the length of a curve. This will be for the surface area. Information on centroids, then separable equations, first order linear equations, and a table of integrals. These are not necessarily saying we're going to integrate a whole bunch, but I'm putting this on every exam, this block right here. Some of the more technical antiderivatives, like say this one, or ones where you just don't have to derive over and over again, since that wouldn't be the point of when this comes up. And then the good old trig table as well. It's going to make it come back on each and every exam. So as you study for this upcoming exam, if you keep this either pulled up on a web browser or printed out, it's going to inform you what you need to have memorized and what is provided. So it's a great way to get started. You don't have to bring it to the exam. Just to clarify, it really is the last page. This is just a redo from exam 1. And this is maintaining the pattern that we did on exam 1 as well. These are the lecture notes converted into worksheets. They don't have answers in the back, but you can go to the lecture notes above and see what the solutions were. Some of the problems in here have been deleted just as a way to say they didn't really make good exam questions. And these are the homework exercises. This one might not be as exciting, but if you want to go back to your homework exercises, they're all here. And if you forgot how this one went, give it a try. It's, excuse me, just as good as it was before. And then for the people who want actually new problems, here's what version 3 is. Some of them are pretty challenging, but it has the problems and the solutions at the back as well. So these are fresh problems. But I should say one more time, the reason I do it this way, I call this a version 1 and a version 2, is because it's my way of saying that when I go to write the real exam 2, these are the problems I'm actually looking at. I go through these documents and I make a selection on these kind of problems. I change the problems a little bit to keep the difficulty the same, make sure the exam doesn't get too long. But the problems in the lecture notes, the problems in the homework exercises really are the main exam questions we're going to be dealing with. And so it also tells you the best way to be prepared for this upcoming exam is definitely to get caught up on these homework problems right here. If you're caught up on those, you're doing second version, and I'm writing the exam based off what you're actually solving here. So that's, if you're short on time, probably the most effective thing you can do to prepare for exam 2. Get as caught up on these as possible. And even if you send me a batch of problems on the 15th of March, that's just a couple days before the exam, I'll make every effort to grade those, get them finalized and sent back to you. Even if you're sending in hard copies, if you send me hard copy work on Thursday, I'll take that work, scan it, send it to your ISU email address so you'll have the feedback on these problems here. I'll better inform you on how on track you are for resolving them again on the real exam. So that's how every one of these exams are going to go pretty much. We'll redo that for exam 3 and the final exam. But any comments or questions so far? Okay, and one other offer. We mentioned this on exam 1, but I didn't have a lot of takers, so we just went right into working material when that happened. But once we get to Thursday of this week, if folks have questions they would like to discuss relative to exam 2 material, whatever it may be, wherever file it comes from, I'm happy to spend some time on that to start off class on the 13th. It can turn into an entire informal review day, or if we spend a half an hour and just run out of questions, that's okay too. We'll just return to whatever the topic was that we had up here. So if you would like to ask some questions as a review on the 13th, that's a great way to spend some time. But I think I ran out of stuff to say. After we finish the exam, we'll have 2 more days this week, then we'll go to a much needed spring break. Then 1 more exam, another filler week in the middle, which is just a catch up on Monday pretty much, and then review the rest of the days. And we'll redo that same kind of information you saw in the final exam down here as well. But I think that's it for all my announcements. Any last questions at all, folks, before we jump back to 11.1? Okay, well, 11.1, we started off pretty slow. We define what a sequence is. It's just an ordered list of numbers, a definite order, and we wonder, does it converge or diverge? That's a major concept we're working on right now, but we found that convergence or divergence of a sequence is practically a full-on redo of the work you did in Calculus 1 on just ordinary limits. It's kind of nice in a way. So we're reviewing a lot of Calculus 1 techniques, but now we're also going to look into section 11.2. In section 11.2, we take a sequence, which is a definite list of terms, and the thought here is delete the commas and replace addition signs. we're adding up all terms of the sequence, and it's an infinite list, so that symbol there is legitimate. That's what we mean by a series. But there's a bunch of mathematical definitions under this that tells us, what did you mean exactly? There's really a limit going on. And so that's what makes section 11.2 kind of technical. We'll take our time with it, work at it carefully, because if we walk away from 11.1 and 11.2, in our head, the wires are still crossed for where it's hard to tell between a sequence and a series, the rest of chapter 11 is a nightmare pretty much. So keeping those concepts separate in your mind makes all of the difference in chapter 11. Well, let's go back to dealing with the sequences. Here's where we left off. We were discussing a really technical theorem, but this theorem was really kind of a way to say, as a guide, anything you did in calculus 1, doing this kind of limit, carries over to calculus 2 when you're doing the limit as a sequence. So that gave us some interesting options on this one. If you're going to compute the limit of this as a sequence, it's an indeterminate form. That means calculus 1 techniques are involved. And you could really redefine a function, f of n. That's what we did. We said f of x takes on this form, which was really just switching x, or excuse me, n for an x. We did the calculus, did the L'Hopital's rule, and found that it diverges. The whole purpose, really big takeaway to theorem 3 is, if you use L'Hopital's rule just on this, and bears repeating, that is okay, that's appropriate. Some people actually do use that extreme abusive notation because they're thinking of theorem 3 working in the background. So even if these were e to the n's and 2 times n's, you could still use L'Hopital's rule and differentiate them, because the only different point of view is x versus n. And this theorem says that's an allowed change of view. Well, pretty much that's what's going on with all of these limit laws. These are the new ones, but take the ones from calculus 1, put n goes to infinity instead, and you're getting the same limit exactly. It's the same concept, really. So let's keep on trying these out. Here's the next one, first one for the day. Theorem 4, and this one's pretty big because it allows us to calculate the limit of these sort of things, rational functions. So what is provided is just a sequence. This is the nth term, a sub n. And when n is 1, it gives us one term. When n is 2, we get another. So it generates out a list of terms like we were seeing in the first problems. But also it's confusing, right? We're saying that this is a sequence because this is one of the, let's see here, several different ways of saying it. List out the terms. Write a bracket with the nth term inside. Do the same thing, but say the index goes from 1 to infinity. But what we did in that problem was we just wrote down an, called it a sequence, so you have to know at the same time. It really means we're thinking of that, a whole list of numbers. Really very vague, right? So that's one of the things that makes this challenging. Standard way to write down a generic sequence is that way, but when you see that, imagine a list of numbers in your head and you're thinking the right thoughts around it. What do we want to do? We want to take, well, geez, that's already vague, right? It just says determine if it converges or diverges. No further information whatsoever on the limit. But in the land of sequences, a question of convergence or divergence is always a statement that goes like this. Limit as n goes to infinity. And the direction's firm too. We start at n as 1 in the sequence, then we have a second term, a third term. We always take the limit as n goes to infinity because we want to know what happens to these terms in the very, very long run. So that's the limit we're taking. We expand this and take the limit as n goes to infinity of n squared minus 3n over 8n minus 4n squared. Then there is one humongous statement in calculus 1 that I feel like it doesn't get enough attention in how impactful it really is. Any limit that involves going to either positive infinity or negative infinity, whether the variable is x or n, is just connecting the concept of a horizontal asymptote. The value of the limit is the horizontal asymptote I mean, if it exists, right? Not every rational function will have one, so we should clarify if it exists. If there is no horizontal asymptote of this function, well, that limit doesn't exist. But we want to further specify in what way did it fail to exist? Did it blow up to positive infinity? If so, we would really write equals infinity. Did it blow up towards negative infinity? We would really write equals negative infinity. So that's if it doesn't have a horizontal asymptote. But this one in fact does. Anyone happen to see what it is just by visual inspection? Yeah. Yeah, good call. I got messed up with that 8 there, forgot the power, so good eye on that. The key fact about this is because there's a tie in degree, n squared above, n squared below, the automatic horizontal asymptote of this rational function, even though it's in variable n, is take coefficient 1 from above, divide by the coefficient -4 from below, and that's a weird format, but I'll leave it just like that, -1/4. So the whole thing converges. And our job is done. Weird, right? I never use that theorem. That's almost unsatisfactory in a certain sense. This is a huge shortcut, but this is also a theorem the author of our textbook states, I think, section 2.4. We should take advantage of it whenever it comes up. But if you didn't see the horizontal asymptote, let's also write out the steps you might take. Let's do this in orange to convey this is actually the way you want to do these kinds of limits when they come up. Because over the course of chapter 11, we're probably doing that limit right there in lecture notes and homework problems hundreds of times. It's not an exaggeration. This comes up all over the place. So you don't necessarily want to take these steps, but this is what they look like. So here's the full steps. This is just a highly encouraged shortcut. Full steps would go like this. We take the limit as n goes to infinity, and in the denominator, we identify the term with the highest degree. Grab just the variable part, n squared, and everything inside of here will be divided by n squared. So let's just write it out to convey what that would look like on paper. Go n squared over n squared minus 3n. Let me fix that formatting. Minus 3n over n squared. Divide by 8n over n squared minus 4n squared over n squared. Then we run a cancellation. We expect quite a bit of them. Cancellations here and here, here and here, leaving a 1 up here. And now it's the limit as n goes to infinity of 1 minus 3 over n, so reduction on that one, 8 over n minus 4. And that's where this limit comes up. Every term here that has n surviving, where the power on n is positive, is going to go to 0 in the limit. But the way to think about what this theorem is saying is, if you're taking the limit as n is going into infinity, and in this term, the numerator is just constant 3, if the denominator grows without bound, it would just mean the whole thing converges to 0. It's getting smaller and smaller, and that's the essence of that theorem there. So this term also gets smaller and smaller. It goes to 0. And then what's left behind is 1 minus 0, 0 minus 4. But those are the same coefficients that we identified here at the very, very beginning. So we get -1/4 out, outright. Well, any questions, folks, on that limit there? So reminder on this one is, it's an important theorem that comes up here and there all over the place. But if you're doing a limit like this, bigger idea is think in terms of the horizontal asymptotes of the function if they exist. Because doing these full steps, of which there are going to be loads of these in chapter 11, it's okay for the first few times, but in really big problems already, you don't want to take and do a whole bunch of big sidelong computations in the middle of a long computation itself. That's the purpose of this shortcut here. But let's try theorem 6 next. This is just like a one big long march from theorem to theorem, seeing what new idea we can discover. Then at the bottom of these notes, we'll just do several additional exercises where there's no theorems, everything's kind of out of context. But this is a nice theorem right here. It tells us if you take the limit of the absolute value of the nth term of your sequence, and if that happens to be zero, then when there's no absolute value whatsoever, you get zero again. It allows us to do limits on these kinds of things, which are pretty tricky in their own right, but also allows us to deal with the shortcut all at the same time. What makes this one a tricky one to deal with is when n gets large, we expect this is getting closer and closer to zero, but also the terms are alternating as a positive term and a negative term, making our thoughts on how this limit really works a little bit more vague. Really though, it's no different than the concept we were saying right here. If n gets really, really large, and you have something that is constant in the numerator divided by something that's growing large, you should get a zero. Why doesn't that concept work here? It's because the numerator isn't constant. It varies, but its size never exceeds absolute value of 1. So it's related to this, it's just not constant itself, because the numerator changes as n changes. But even still, we're going to try to relate this concept to this one after we look at the official method. The official method is to use the theorem and go to an associated sequence, absolute value an. So we could start by saying, let absolute value of an be equal to the absolute value, -1 to the power of n, divided by n plus 4. When you go to take this absolute value, let's take a couple steps with this, because we'll do some of this work in the later parts of chapter 11. You can break up the absolute value function as affecting the numerator and denominator separately. But I claim n plus 4 in absolute value is automatically n plus 4. That's not necessarily true, because that could be negative, right? And then I have the wrong thing below. But if the question is about convergence or divergence, then we're dealing with a limit as n goes to infinity. That means this is guaranteed positive. N is a large value in the actual domain where we're working with n. So it's appropriate to drop absolute values down in the denominator. Now in the numerator, absolute value of -1 to a power, that's just 1. So what the theorem 6 is saying is, if we are worried about the non-constant nature of the numerator, the fact the numerator does vary, it alternates, that's okay. You have a new method. Take the absolute value of the whole thing and do the limit of this. Notice the conclusion is specific. If you get 0, then we can conclude the original sequence itself has limit 0 as well. If we get like 5, this theorem is not going to help us at all. There's no connection then with the original sequence over here. So let's do that. Let's take the limit. Let's say here then, limit as n goes to infinity of absolute value of an equals limit as n goes to infinity of 1 over n plus 4. And that's a rational function. It, in fact, has a horizontal asymptote. Anyone happen to know what it is? It is 0, absolutely. It's weird because we're thinking of it along the lines of what we were saying here, right? That's another rational function. Its horizontal asymptote was found by comparing coefficients in numerator and denominator. Why is it different here? There's no tie in degree. Numerator is of degree 0, denominator is of degree 1, and this conveys the limit is 0 just automatically right here. So we could say 1 over n plus 1 has horizontal asymptote y equals 0, since the denominator, that's such a long word, denominator split over across 2 lines here, has higher degree. So the higher degree part was just that part right there. But going back to the original problem, here we took a shortcut. We know we have a horizontal asymptote, should give us a value of 0. But that was for the absolute value of an. So we can come over here and say, therefore, limit as n goes to infinity of an, which is the limit as n goes to infinity of the original thing, -1 power of n plus 4, it has to be exactly the same. Once we got 0 for the absolute valued sequence, we get 0 for the original sequence itself. It's as if it's now squoze into the position of 0, whereas this one here with absolute value gave us 0, forces us in that way to get 0 as well. Well, any last questions, folks, on doing this limit here? So what's the purpose of Theorem 6 is another thought. The idea with Theorem 6 is this limit, where I've circled as n goes to infinity and boxed out the 3 over n, is the concept that if you're constant in the numerator, the denominator grows without bound, you get 0. And Theorem 6 kind of weakens that thought. If we have something that is, well, not necessarily constant, but it can never exceed a positive value. It can't get larger than 1. It's bounded as a value. So it's not constant, but it's bounded. A bounded value in the numerator, whereas your denominator grows without bounds towards infinity, gives that as a foregone conclusion. So anytime you see this come up, and there'll be plenty of times, here is the highly encouraged shortcut. Essentially, what these theorems and examples are all about so far is things you are allowed to take for granted, that you don't have to show the details every single time when it comes up. And this is one. If limit n goes to infinity of -1 power of n divided by n plus 4 comes up, and you've recognized that this is bounded in the numerator, let me just spell bounded right first. There we go. Bounded in the numerator and grows without bound in the denominator, then instead of doing these weird backflips of going to the absolute value sequence, you can conclude here and then, just right at that spot, limit has to be 0. That would be the correct mathematical assumption to make at that point. Well, that's another theorem down, another concept out of the way. Some of these are going to get a little bit more interesting as we go, but again, at the moment, all of these examples are completely just about things you're allowed to take for granted, and probably should. When it says highly encouraged, this is just to make the life more easier. So we're focusing on the actual series, sorry, forgot the word, rather than the small minutia of dealing with these limits here in the sequences. But here's our next one to take a look at. It says, if the limit of n goes to infinity of a sequence an is L, and this is one of my favorite properties of continuity, the function is continuous at L, then any function of that sequence would be a function of the limiting value. So this statement here is phenomenal in a certain sense. It allows us to do one extra thing with our limit. Essentially, what this is saying is that the limit as n goes to infinity of f of an, because of continuity of the function f, the limit operator can commute inside. That's really the major content of this. And it kind of gets lost in translation when it's written this way. So this is my preferred way to say it. Let me do a arrow that goes both directions. These are equivalent statements. This is equal to the function f of the limit as n goes to infinity of an. So the continuity property tells us limit operator commutes inside the function itself. Kind of a slick process, and it is definitely relative to this one. Let me make that a little bit bigger so we can actually see this. The continuous function in this problem that we're looking at is the base e exponential. E to the x is continuous for all values x. And it already feels weird, right? We're talking about a continuous function, even though an as a sequence is discontinuous. We're just talking about one element, the function, and then the sequence inside of it. So we can write over here to the right, y equals, let me write it slightly better. F of x equals e to the x is continuous on R, meaning it's continuous for every single real number R from negative infinity to positive infinity. So we definitely have a continuous function. And that allows us to do this. That means we're basically done with the limit. We can go and fix those characters. Limit as n goes to infinity, e to the power of 4n plus 3 divided by 2n minus 1 becomes e to the power of the limit itself. That's us writing it this way, the limit going inside the function e to the x. Limit n goes to infinity, 4n plus 3 divided by 2n minus 1. And now as we look at that limit, this is a rational function. We have a tie in the degree. Let me say it this way. Tie in degree. What I mean by that is the highest degree term in the numerator is degree 1 from 4n, degree 1 for 2n in the denominator as well, so that's the tie. And whenever we have a tie in degree, that's the whole punchline to the limit, 4 halves. So through our shortcut, we get e to the power 4 halves, which is e squared. So we would say for this problem, converges. So it's a convergent sequence. It would have been kind of tough to work with it because there's lots going on with it. But the whole punchline to it is it's just e squared. It's as if we took a problem, take the limit of this, but then made it a power on e, and now it's a bigger problem. But if it's a continuous function, there's not much going on. The limit just affects what's inside. And let me double check something. I think I forgot a word here. This word is actually important. Don't let me forget this. I should have said converges. Actually, let me say it down here where we're doing their main sequence. Let me double check the rest of them. Okay, I think we got it on the others. Well, any questions at all, folks? So I'm running through this one. Looked like it'd be the worst problem of the day, but this is another big takeaway. Even if you didn't show the step of the limit coming inside, just know that the limit is only affecting this part, and it's correct to say it's now e squared. That is the right mathematical leap to take. Theorem 7 says you can take that for granted as well. Kind of nice in a way. And finally, here comes theorem number 9. Theorem number 9 is going to get reused in section 3.2. This is tied in together with the so-called geometric sequence, or excuse me, geometric series. This would be a geometric sequence, but our author didn't decide to define it that way, unfortunately. But it's a pretty special sequence, and here's the idea behind it. You take R. R can be anything, but if we're thinking about convergence, we want R to be in these bounds specifically, strictly larger than -1, and then up to, but including +1, would make this converge. Kind of strange when you think about all those conditions all together so far. Divergent for all values of R. And this theorem doesn't just tell us when it converges and when it diverges. It gives you the actual values it would converge to as well. It says, moreover, here what we're taking is the domain where it converges on and just splitting it into two cases. If you're strictly between -1 and +1, it will converge to 0. But if it's exactly 1, well then 1 to any power is just 1. This is a sequence of just 1, 1, 1 forever. The limit should be 1 because there's no change at that point. So that's what's going on with this theorem. Well, honestly, I think it's kind of a confusing theorem. So any questions about it at the moment? Let me make this design choice up to the class. Should we plot this for different cases of R? Or does this feel like it's concrete enough with what we're seeing here? More graphics or dive into the problem? It's kind of weird being the decider, right? How about for someone over Zoom? Let's make someone over Zoom decide this for us. For folks in Zoom, since it seems like we decide these things mostly with people physically in class, let's pick a direction. Should we illustrate this a little bit more, or should we go directly into the problem? I think we should sketch it out. Thanks. I was going to say, let's do a tiebreaker. We can flip a digital coin, but I appreciate the comment in class. Let's go for sketching this out. It's always weird trying to pick a direction to go in a math class, right? Excel. This is just the quickest way for me to try to graph something like this. Probably there's a great way to do this in Desmos, but I've never had the time to look into it. Oh, I just noticed some chats. Awesome. Let's do the illustration. Sorry, Easton, looks like a couple people beat you on that. We'll do a quick illustration, not take too much time, and then go right into that problem. And looking at those timestamps, I think there could be some lag on Zoom. I think I did see these chats a little bit earlier than I realized, and they just didn't actually show up here. Sorry for that. Lag is a little bit weird dealing with these online settings. So if we're going to do this, what should we pick? Well, we need to first have an index n. Then we have to have r to a power of n. So this will be r to power n. Now on this one, let's go 1, this plus 1, and we should get a good view of what's going on with the first 20 terms. And on this one, we need to pick a value. Let's pick something for convergence. So I'll pick the value to be, let's say, how about a negative 0.3, raise it to a power n. The power n is on the left. So that'll be a2 on that one. And this is what you would get. But then when you go to this one, that's going to be r squared. You're multiplying negative 0.3 by negative 0.3. It's alternating and turning out positive next. And as this continues to run through, we're getting scientific notation really rapidly to say these are essentially 0 for all intents and purposes at this stage. We should be able to get a really quick graph as well. I think that was in insert. Thanks, I was just reminding myself. I usually try to find it somewhere in data. That seems like it makes sense. And this is the view of that sequence. It jumps all over the place. Oh, don't mean to do that at first, but when the terms get larger, it very quickly approaches the x-axis in this way for convergence. But now change this a little bit. Let's say it was negative 0.9999. That's still in spec for convergence. It's got to converge to 0. But what's the speed of the convergence? Pretty slow. I can't even see it on this graph. I'm going to need potentially thousands of terms to show that these dots actually get close to the x-axis because it was so close to negative 1 in the first place. So the closer you get to negative 1, the slower the convergence is. And if you really hit negative 1, here's what happens. Just throw in negative 1. And we have a legitimate alternating sequence. That didn't work out. Let me try again. I think I have to go like that. There we go. We have a legitimate alternating sequence going from positive 1, negative 1. Almost doesn't even look like the graph changed at all, right? This is divergence of the sequence. And it's divergence in the weirdest sense. It's not diverging because it goes to positive infinity or negative infinity. It's diverging because it's alternating for all of time. And this gap we see in the middle never goes away. It's always going to alternate by a distance 2 from one term to the next. So that means that's what's going on with divergence. Let's do one last one for convergence. It was, say, 0.5. Then that's your first term there. And we get really rapid convergence because on term 2 of this sequence, when r is 0.5, it's giving us 50% of the prior term. On the third term up here, you're multiplying by r again to get r cubed. It's taking 50% of the prior term. So we're cutting it in half every single step, making it converge to zero very, very rapidly. Even if this was negative, we'll change the view of what we see, but it's not going to change the fact it's converging or the speed of the convergence. It's alternating, sure, but the gap between the dots as it approaches the x-axis is shrinking to zero. So that's why the limits right here would be zero even in that case. So that's what's going on with all this information right here. And notice what they provided for us, the nth term of the sequence, doesn't even fit in this format. So we're going to start this problem by just correcting a little bit. We want a common ratio r to a common power n. We don't want to mess with all of this stuff here and try to apply it to theorem 9. It's just the wrong setting. So first is some algebra. We take an. We want to bring all the powers down to just power n. So factor the 4n plus 1 as 4 times 4 power n. Divide by negative 5 to power of n. Then this value 4 could be written in front. And everything with power of n, we can do another kind of factoring. Exponent goes on the outside. 4 stays here. Negative 5 goes here. And what this exhibits is the actual common ratio r. Let's re-highlight this. We have a value for r now. We can say here, r equals negative 4/5 implies it is certainly between negative 1 and positive 1. Written in a weird way, that or equals is just reminding me that's where it converges as well. All I'm saying right here is that's the condition for convergence up here. And now we can conclude the whole thing by saying, therefore, limit as n goes to infinity of a sub n. By our work above, we can throw 4 in front and take the limit as n goes to infinity of negative 4/5 to the power of n. Double check our case-wise output for the limit. We're in this region where we would get a value of 0 because we don't have exactly 1. Let me try again. 0 because we don't have exactly 1. There we go. And so that means it converges. And that's pretty much the whole problem. All we had to do is do some exponent work on this so we can see exactly what n really was. And then even with this constant 4 here, it's irrelevant because it's going to be multiplying 0 that we get through the limit. So we'll come back to theorem 9. This is a component of the geometric series that's coming up next. But at the moment, it's just kind of a side thought. If you come up with these exponential expressions, this is a nice little tool to evaluate the limit right away. It's the first theorem where this one is not stuff you could take for granted. It's a legitimate extra tool in our tool shed for dealing with these limits. Well, these are all the theorems that are in this section that I felt like we should really pay some extra attention to. Next thing we're going to do is just take a whole bunch of limits, starting off here on example 4. Any questions at the moment so far? Maybe before example 4, I threw in the screenshot here from assignment number 11, mainly to talk about what I was saying here about correct limit notation. The correct limit notation is just this requirement right here. That the moment that we write out a limit, we actually have to have the limit statement right in front. I mean, we should have it the whole time, but at least at the last step, we should really emphasize it. The goal here is connecting this comment in red. We cannot say that 4 negative 4/5 n equals 0, because this is not what we mean whatsoever. The thing on the left is an algebraic expression, and pick any value for n, it's never 0 whatsoever. So it misses the idea of what we're really trying to compute. We must say that it's the limit as n goes to infinity of 4 times -4/5 to the power of n equals 0. It's the limit operator in front that actually makes this a legitimate equation. Here, this is just outright false. As an algebraic expression, as an idea, it's not what we were meaning to say in the very first place. And really, this is a big statement in red because it's just going to come up in a lot of different kind of formats, especially when we get into sections 11.2, 11.3, and so on. Limits are going to come up all the time, but if we forget the limit was there, it's so easy to lose our way and not even realize what the major goal was in these kind of problems. So it's not going to be worth a lot of points. If you wrote this on your homework exercise, I'll write the limit in front. You might lose a point, and I'll say we need to say write in correct limit notation. It's not going to be something major. It'll be like a reminder. But you don't want those kind of reminders when you're doing it as an exam problem. It feels like it's higher stakes at that point. So with that comment out of the way, we'll determine if these sequences converge or diverge. Now it's like generic homework problems like you're going to be seeing as well. And this one's weird, right? It's the factorial function. We want to take the limit as n goes to infinity of the ratio of expressions on factorials and see what that will come out as. Weird problem out of nowhere. So before we even get started, we should play around with what we mean by factorial functions to get an idea of how we're going to work on this. So first, by factorial. This is just a way to re-express a kind of multiplication where you go 5 times 4 times 3 times 2. And I always thought this is curious. Even though you don't have to say times 1, it's a good idea, it turns out. So this is just repeated multiplication where this is 20, 60, 120. It's a function that grows extremely rapidly because 6 factorial is this number times 6. So in other words, 6 factorial equals 5 factorial times 6, which means it's 120 times 6, which means this is getting large really quick. Let's see, 12, carry the 1. I think that's 220. And that pattern just keeps on going forever. Oh, 670? How does that sound? It can't go 720. Thank you for that weird multiplication there. It comes out as 720, grows even faster than we might have thought on paper with that correction thrown out of there. So if we did 7 factorial, it's getting just too annoying to even do by hand, right? This grows extremely rapidly. But one takeaway from this is you can factor down your factorials in any way that's convenient to you. So for example, you could take n factorial. N factorial is n times n minus 1 times n minus 2 times, the 3 dots here are a way to say and so on, 3 times 2 times 1. So that's just a way to write n factorial. Loads of other ways. You could write out n factorial is n times n minus 1 factorial. That looks weird, but this is actually the concept that we need to help us out up here. How does that work? Well, n factorial itself was n times all of this stuff. And all of that stuff is just another way to say n minus 1 factorial. Because you start at the number or the expression, whatever it is, you write it down, then you write down the next expression, 1 lower, much like the 5 times 4 times 3 times 2 times 1. So n factorial itself can be brought down, factored, in whichever way is convenient. You could also factor this as n factorial as n times n minus 1 times. Exactly, anything like that would work out. So with that information, we can come up here and do some interesting factorial work on that expression. Let's begin by writing an equals. You want to look at the one that has the higher expression. By higher, I mean this one is at, oh, this is hard to highlight, 2n plus 3, whereas the denominator is at 2n plus 2. We want to break down the one that's a little bit higher, write it in as 2n plus 3 drop it down by 1, 2n plus 2, but then stop right there. Throw the factorial on it, because now the denominator being 2n plus 2 factorial tells us we have a humongous cancellation right here. This will cancel with this. That means when we're taking this limit, it's just for 2n plus 3, nothing else. Kind of weird in a way. And you know what's also weird is factorial coming out of nowhere is because that's what we're getting into at the end of chapter 11. Somehow when you deal with Taylor series and Maclaurin series, every Taylor series, Maclaurin series problem has factorial come up, guaranteed. Now that's really, really weird, but that's just the nature of, it has to do with the derivative coming up itself. So we're crossing that bridge a little bit early by working on factorials right now, not waiting it for it being an extra concept at the end of chapter 11. Now all we need to do is take the limit as n goes to infinity, where it says correct limit notation, that just is a reminder, we really need to write out that we're taking the limit of something on paper. So there it is. We're taking the limit of an, but by the work above, this is the limit as n goes to infinity of just 2n plus 3. Well, as n goes off to infinity, so does 2n plus 3. This just goes larger and larger, even faster than n is. We're doubling it and then incrementing by 3. So this limit doesn't exist. But we want to say something even stronger than that. We'll say equals infinity, and so it diverges. So even when the limits don't exist, if we can put an infinity on there or a negative infinity, we must do so at that last step, because that's more information than just simply saying does not exist. This is the way in which it fails to exist. We're saying that just gets larger and larger without bound as n gets larger and larger itself. But we did it, folks. We have worked through the factorial information. We've worked out the limit, did the so-called correct limit notation. Any last questions or comments on this one? Okay, now when it comes to correct limit notation, I want to be straight up honest with you. There are stylistic choices to this. So if you wrote out your problem like this, an 2n plus 3 factorial, 2n plus 2 factorial. Then you start working with it algebraically right here, 2n plus 3, 2n plus 2 factorial, 2n plus 2 factorial. Did your cancellation and got your expression 2n plus 3 factorial. We can make this correct limit notation, but here is the other stylistic way to show that. We'll say that this diverges to infinity as n itself is running off to infinity. So this is a different view of the so-called correct limit notation. Our author doesn't use it a lot, but if you really scan his pages, he does use it. So what made it correct limit notation was we showed that this is going to infinity as a limit. And we also showed the other key part of the limit. This happened as n itself goes to infinity. Sometimes people find this is a slick way to do it because now you're not copying limit as n goes to infinity, line by line by line, until the very end. So this is just another stylistic way to express correct limit notation. Well, we did it, folks. This was kind of a tricky problem. It has a lot of objectives we're trying to solve all at once. Major takeaway about it is really working with the factorial function. This is our first early look. But now let's go off to our part B on this one. New sequence. Whole goal is here to determine if it converges or diverges. Should say it here. This one diverged. And this one is a little bit odd. We have a continuous function, natural log. Its continuity goes from 0 to infinity, but the limit is always as n goes to infinity. So we are not too worried about where the domain ends. But there's two functions here, so working on this limit is actually problematic. As n goes to infinity, so does natural log n plus 1. As n goes to infinity, so does natural log n, and that means lim n goes to infinity, an is of form infinity minus infinity, and that's not good for us. That's an indeterminate form all out of nowhere. We cannot do this kind of arithmetic on infinities. If it was a plus, we would just say the whole result's pos infinity. But this is now indeterminate. It could equal 0. But if the growth rate here is slightly higher, it could be any finite number, maybe e or 2, something weird like that. If for some weird reason, imagine a different function, this grows faster, it could be some negative constant, or maybe negative infinity. So anything at all could happen. The answer could be positive infinity, negative infinity, or any finite number whatsoever. We have to resolve all of that once and for all and get out of the indeterminate form at the same time. Meaning it looks like a L'Hopital's rule problem potentially, depending on what we do. Anyone see something to try on this? It's kind of weird in a way, right? For using L'Hopital's rule, we want infinity over infinity, or 0 over 0, which means we'd rather have fractions here.
Well, the natural log.
Absolutely. So that's the major idea we need. We can't make a fraction out of it just like that, but we can use properties of logarithms like you were saying. So this is the key to this whole problem. I think this happens in the homework as well, so it's also here for that purpose. Use a property that natural log A minus natural log B is the natural log of A over B. You get a fraction out, and you know what? Once you form that fraction, the indeterminate could go away because the indeterminate was because there was 2 natural logarithms. Now we're going to have just 1. So let's write in an is natural log n plus 1 divided by n. Now, in this configuration, we don't have an indeterminate form whatsoever. Well, I mean, you kind of still do. You could say this is infinity over infinity, but we don't need that information because we can resolve this limit really fast without using L'Hopital's rule. We can say limit n goes to infinity of an is limit n goes to infinity of the natural logarithm n plus 1 over n. I'm going to take an additional step and use the fact that the natural logarithm on the domain we're interested in, going from, say, 1 to infinity, is continuous. The continuity of the natural logarithm allows us to go the natural logarithm of the limit itself as n goes to infinity of n plus 1 over n. So this step is by continuity. So now that we've got to that step, we just have to resolve this limit right here. But we're back in the land of analyzing a rational function, a tie in the degree, and the coefficients here are 1 and a 1. That means by our shortcut, this limit is essentially completely resolved. This becomes natural logarithm of 1 over 1, which means we're doing natural log of not 0, that'd be bad. Let me fix that. Natural logarithm of 1, which now itself is 0. Tells us, well, thinking of infinity minus infinity as working ordinarily with arithmetic and getting 0 did work out in this case. But I assure you that was not something that always happens. There's plenty of problems where this does not occur. But we've got it, folks. We have a value of 0. It's a number. We didn't get infinity or negative infinity. The fact that we got a number says this whole thing converges. Any questions at all, folks, on the last work here? Kind of weird because there's not a whole lot to do. Once you get through the weird difficulty, whether it's simplifying the factorials, dealing with the properties of logarithms, really not a whole lot less to show. So that gets us to the one that's a little bit nastier. Sine of n pi over 2. Now imagine you're going to just follow this on the same kind of way that we've been doing all the problems. Take the limit as n goes to infinity of an, which means we want the limit as n goes to infinity of sine n pi over 2. What would we do next? I'm going to write down something that I'm going to erase immediately after. You don't have to copy it in unless you want to say what not to do. But one thing that we sometimes put down on paper because it feels natural, and sometimes it works out, honestly, is this. We might write sine infinity pi over 2. But this as a statement has no meaning. It's kind of rude to say, but this is really an entirely meaningless statement. The reason for that is sine is a mathematical function which takes as its domain a real number. That's not a real number whatsoever. Infinity is not a number, it's just a mathematical concept. So this isn't going to help us one shape at all. And so what we have to do is, well, I don't know, something else. If that has no meaning, we need to go back to the sequence and really look at it further. Anyone see something else to try with that sequence an? The sad thing about n right here is because of the sine function, it's pretty much captured inside of it. We can't factor it away. It's now like a feature of the problem, unfortunately.
Well, the sign is oscillating between 1 and -1, that means it just diverges.
Exactly what's going on, exactly. So if you could take this information, imagine in your mind, what do the terms look like? Like you said, it's oscillating between +1 and -1. That's the whole trick to this one. So let's take another view of this. Because the sine function came up, let's throw it a unit circle. It's at n pi over 2. Well, n starts off as 1, right? And when that happens, it's pi over 2. When n is 2, we're at pi. When n is at 3, we're at 3 pi over 2. When n is at 4, we're at 2 pi. And we just keep going all around the unit circle in that kind of way. Because the sine function came up, what we care about most is second coordinate. So let's write in those second coordinates. I want to write in the first coordinate first, so it's not ultimately just confusing. This goes, let me try again with the first coordinate, 1, 0. This coordinate is going to be 0, 1. This is -1, 0. And this one is going to be, I'm going to blame daylight savings on my coordinates, 0, -1. Does that look right to folks? Okay. Now, once we have all that, we can come back and actually use our alternate notations for the sequence. This is just saying what the nth term is. Writing it out this way is us saying as precisely as possible that this is just a list of numbers starting at 1, going off to infinity. And now, here's how the numbers progress. When n is 1, we're up at pi over 2, and we grab our second coordinate, 1. When n is 2, we're at pi, second coordinate, 0. At 3, second coordinate is -1. At 4, second coordinate is 0. And this entire pattern repeats without fail, no change whatsoever. So 1, 0, -1, 0. And I'll just go ... to convey that's the whole pattern right here for our sequence. And then over here, we get to say, well, not infinity, not negative infinity, nothing like that. We'll say, does not exist. This is a callback of an acronym from Calculus 1. DNE is just shorthand for does not exist. So many mathematical concepts you write down on paper, if the conditions are right, they don't exist at all. So it's kind of funny that that became an acronym in Calculus 1. So it does not exist. we need to explain why, but this is the explanation. We'll say because the sequence oscillates between -1, 0, +1, and how should we say the last step? Unending, always, for all values of n, anything like that would be just fine. I'll go with for all values of n. So we have a conclusion to the limit. This is the first time in this entire class, I think, we've said does not exist outright on a limit. We have the explanation, but one last thing still missing on this. Anyone see what the last part of the conclusion is that's still not on paper? Good call. This is one of the weirder ways it diverges. Doesn't diverge because it blew up towards positive or negative infinity. It's diverging because those are the only terms you get. It never is settling down on a real number specifically. So diverges. I really thought somehow we'd get into section 11.2, but not at that pace we were working on. I'm going to blame daylight savings again on that, but any last questions or comments so far, folks? Okay, when we come back next class on Wednesday, we'll start working on our way through section 11.2. Really doubt we'll finish it. So when we come back again on Thursday, that's a good opportunity to ask some review questions to exam 2. And when we run out of time, we'll just go back to the 11.2. But have a great night, folks. I'll talk to you all later.
It has certain pieces for it. Yeah. The way you give it to visual, yeah, I mean, I think that would.
Thanks, you too. Take care.
Test on Tuesday.
Sorry, say again?
Thanks for letting me take the test on Tuesday.
Oh, yeah, absolutely. No worries.
Yeah.
Yeah, I remember you talking about that, I think, weeks ago as well.
Yeah,
That's make perfect sense.
Tuesday.
Dang it. Yeah, and no worries. If anything random occurs on Tuesday, we'll stress out about it a little bit, but we'll make it right.
Yeah.
So there always is opportunity to get it to go through.
Thank you.
Yep, absolutely. You too.